Hello, and in part 2 of this talk about the noise performance of the inverting op-amp amplifier, I'm going to be putting in some actual values and seeing which of the noise sources provides the largest contribution to the output noise. First, a quick reminder that if we want to add up the effects of two different noise sources, we have to combine the squares of those noise voltages. The reason is that if we take two noise signals, Ni and Nj, square them and take the average value of that to work out the average power in the noise, then we get this term here in Ni of t times Nj of t. And if Ni of t and Nj of t are independent random noise sources, then if you multiply them together, they're going to be positive the same amount of time that they're negative, and the average value is going to be 0. Just gives us this result that the total noise power in the sum of two noise waveforms is the noise power in one waveform plus the noise power in the other waveform. Okay, let's go back to our inverting op-amp amplifier. There are a total of 5 different noise sources, 2 equivalent input noise currents and 1 equivalent input noise voltage of the op-amp, and the 2 resistors, the feedback resistor R2 and the input resistor R1, both have equivalent input noise voltages. To combine the effects of all of these noise sources, I have to square them, add up the squares of the noise voltages and take the square root of that, and that gives me the total noise at the output of the op-amp. Right, we've already seen that N1, which is the noise contribution of the equivalent input noise current on the non-inverting input of the op-amp, makes no contribution to the output noise at all. It's just 0. N2, on the other hand, which is the effect of the input equivalent noise current on the inverting input of the op-amp, in this circuit does have an effect on the output, and it's given by In squared R2 squared. N3 is the effect of the equivalent input noise voltage of the op-amp, and that's given by En squared times 1 plus R2 over R1, again all squared because I want the square of the noise output. The effect of the feedback resistor R2 is 4kT times R2, and the effect of the input resistor R1 is R2 squared 4kT over R1, because this is multiplied up by the gain of the op-amp, which is minus R2 over R1. All of these have units of volts squared per hertz. If I add them up and take the square root, I'll end up with something with units of volts per root hertz. Now, you can see that the biggest contribution to the total output noise is from this term here. That's the term due to the equivalent input noise voltage of the op-amp. And the second largest term is from the input resistor here, R1. Now that's a useful thing to know, because it tells us if we want to reduce the noise of this circuit, the first thing we should be doing is looking to find an op-amp with a lower value of equivalent input noise voltage. And the second thing we could consider is looking at reducing the input noise from the resistor R1. And we could do that by reducing the value of R1. We could, for example, take R1 down to 1k and R2 down to 10k. We'd still have a inverting op-amp with a gain of minus 10, but we would have lower noise at the output. Now this calculation is fine, provided we're only interested in frequencies at 1 kHz and above. And the reason is that at 1 kHz and above, all 5 of these noise sources behave like white noise sources. The amount of noise that they introduce in a 1 Hz bandwidth is not a function of frequency. However, we know that for one of these noise sources, the equivalent input noise voltage of the op-amp, which is our dominant, our largest noise source, that's not true for frequencies below 1 kHz. From the op-amp datasheet, we can see that as you get below 1 kHz in frequency, the amount of noise contributed in a 1 Hz bandwidth from that equivalent input noise voltage starts to increase quite significantly. So if we wanted to know what the total noise at the output of this inverting amplifier was going to be over a frequency range of, say, 10 Hz to 20 kHz, we would have to consider this 1 over F noise, this flicker noise, as well. So how do we calculate the total noise from 10 Hz to 20 kHz? Well, I'll just consider the dominant noise sources. I will neglect these much smaller noise sources due to the equivalent input currents and the feedback resistor, and just look at the noise from the input resistor R1 and the equivalent input noise voltage of the op-amp En. Now, the noise coming from R1 is white noise. So if I wanted to know the total noise voltage that comes out of R1, then I would just take the expression R2 squared 4kT over R1, that's in volts squared per hertz, multiply that by the bandwidth between 10 Hz and 20 kHz, which is 19,990 Hz, and that would give me the total noise voltage squared over that frequency range due to the input resistor R1. And we can work that out. That's just 100k squared times 4 times the Boltzmann constant times 290. We'll just assume that everything is working at the standard temperature of 290 Kelvin, divided by 10k times 19,990, and that gives 320 times 10 to the minus 12 volts squared. Contribution to the output noise voltage of the input resistor R1. Now, the contribution of En, the equivalent input noise voltage of the op-amp, we have to divide that up into two frequency bands. We know from the datasheet that from 10 Hz to 10 kHz, the total equivalent input noise voltage is 4 microvolts. So we could take that 4 microvolts, multiply it by the gain that this circuit gives to that voltage, which is 1 plus R2 over R1, or in this case 11, giving me a total of 44 microvolts. And if I take that 44 microvolts and square it, I get 1,936 times 10 to the minus 12 V squared, as the contribution in the frequency range from 10 Hz to 10 kHz of this equivalent input noise voltage. Now, I also have to consider the frequency range from 10 kHz to 20 kHz. And I can do that because I know that the equivalent input noise voltage for this op-amp is white in that frequency range, and it's 18 nanovolts per root hertz. So if I take 18 nanovolts and multiply it by the square root of the bandwidth from 10 kHz to 20 kHz, which is 10,000, that will give me the total noise voltage, equivalent input noise voltage, due to the equivalent input noise of the op-amp in that frequency range. The square root of 10,000 is just 100, so that would give me 1.8 microvolts. And I need to multiply that by the gain that the op-amp would give to that noise voltage there, and that's a gain of 1 plus R2 over R1, or in this case a gain of 11, so that would give me a total output noise of 1.8 microvolts times 11, which is 19.8 microvolts. And if I square that, I'll get 392 times 10 to the power of minus 12 volts squared, as the square of the voltage due to the noise contribution of the equivalent input noise of the op-amp over the frequency range from 10 kHz to 20 kHz. To work out the total noise in the range from 10 Hz to 20 kHz then, I have to add up these three contributions. The noise due to the input resistor over that frequency range, 320 times 10 to the power of minus 12, plus the noise due to the equivalent input noise of the op-amp over the frequency range from 10 Hz to 10 kHz, or 1396 times 10 to the power of minus 12, and the noise due to the equivalent input voltage noise of the op-amp between 10 kHz and 20 kHz, which is an independent noise voltage from the noise at the lower frequencies. That would give me another 392 times 10 to the power of minus 12. And they're all in units of volts squared. If I add up these, that would give me a total of 320 plus 1936 plus 392. And if I take the square root of that, gives me a total output noise which would be 51.46 microvolts. The square root of 10 to the power of minus 12 is just 10 to the power of minus 6, so that gives me that micro there. That suggests that the total amount of noise output from 10 Hz to 20 kHz that I could expect from this op-amp amplifier is about 51.46 microvolts, assuming I've got my maths right. Now that's an inverting amplifier. If we look at a differential amplifier, then things get a little bit more complicated. Both equivalent input noise currents of the op-amp now do make a contribution to the total output noise, and we have 4 resistors in our circuit, each of which is making a contribution as well. So we have a total of 7 noise contributions, each of which have to be calculated. However, we could take a shortcut and learn some of the lessons from the analysis that we've just done on our inverting op-amp and conclude that it's very likely that these are going to be the dominant noise sources. The 2 input resistors, R1 and R3, and the equivalent input noise voltage of the op-amp EN2. And we can calculate their effects, put in some typical values for a different op-amp in this case, and come up with a value for the total output noise of this circuit, in this case, microvolts. We'll be having a closer look at the differential amplifier circuit in the next one of these talks, where we're going to see how the simulator can help us analyse the noise performance of op-amp amplifiers. For now, that's all the theory and algebra we're going to do about op-amp amplifier noise models.